Just like with resistors, we can combine capacitors both in series and parallel and find the combined capacitance. So let's connect two capacitors in series. C1 and C2. Now the combined capacitance is given by 1 upon C equals 1 upon C1 plus 1 upon C2. And if we were to have more capacitors in parallel, you'd add up the inverse capacitances. This is the opposite to how you add resistors in series. I'll show you why this is the case in just a second. However, if I was to connect two capacitors in parallel, like this, C1, this would be C2, then the combined capacitance is simply C1 plus C2. Again, the opposite for when you combined resistors in parallel. Why is this the case? Well, due to the conservation of energy and therefore potential, the potential across the first capacitor plus the potential across the second capacitor is going to be the same as the potential across both capacitors. So V is equal to V1 plus V2. But we have the definition of capacitance, which is capacitance is Q over V. So the voltage, or the potential difference rather, is going to be Q divided by C. So this is going to be total charge divided by capacitance equals the charge on capacitor 1 divided by capacitor 1 plus the charge on capacitor 2 divided by the second capacitance. Now the thing you have to know is that we have the same amount of charge. Say if I had 4 charges here, due to arguments of equilibrium, I have to have the same amount of charge on this plate, negative charge, but I also therefore have the same amount of charge on this side of capacitance 2 and the same amount of negative charge on this side. So we have the same, which is the same as the total charge in the whole circuit. So that's why the charge on capacitor 1 is the same as the charge on capacitor 2. So we basically have a common factor to each of these terms, which is Q, which we can replace with a 1. So we get 1 upon the total capacitance is 1 upon C1 plus 1 upon C2. However, when we connect the circuit in parallel, I know that the current flowing through here is split into down these two branches into I1 and I2, because current is charge divided by time. I have the total charge going in here is equal to charge going down the first branch. Just switch the notation here, so call this 1 and this one 2, plus the charge going down the second branch. But due to the conservation of charge law, the total charge is just going to be Q1 plus Q2. So why is the capacitance equal to C1 plus 2 in parallel? Well, because I know from conservation of charge reasoning, the total charge is Q1 plus Q2, and from the definition of capacitance, C equals Q over V, the total charge, Q, therefore, is C times V. So this would be C times V equals C1 times V1 plus C2 times V2. But the potential across, if I was to measure the potential across both capacitors, because they're connected in parallel, they have the same potential. So V1 would be the same as V, as would V2. Therefore, I can cancel V's on each terms, which gives me C equals C1 plus C2 when connected in parallel.